take a deep breath, feeling your chest rise and your shoulders soften, and let your body settle into the quiet stillness of this moment. As you exhale, imagine the air around you growing crisp and thin, carrying the scent of ancient granite and melting snow as we begin our journey into the high, silent world of alpine lakes. What is fascinating about these high-altitude waters is that they exist in a state of suspended animation, often perched more than 10,000 feet above sea level in what scientists call the nival or alpine zone. Here, the atmospheric pressure is significantly lower than at sea level, which changes the very way oxygen dissolves into the water and how sound travels across the surface. When you stand on the shore of a high-altitude tarn, a name derived from the Old Norse word tjörn, meaning a small mountain lake, the first thing you notice is the silence, which is a physical presence. Because the air is less dense at these heights, sound waves do not propagate as easily as they do in the heavy, humid air of the lowlands. You might hear the distant, metallic tink of a single pebble falling into the water from a mile away, a sound that carries with startling clarity across the glassy surface. The color of these lakes is perhaps their most striking scientific feature. If you were to look at a lake like Lake Louise in the Canadian Rockies or Moraine Lake, you would see a blue so vibrant it looks almost artificial. This is due to a phenomenon called glacial flower. As glaciers move slowly over the mountain's bedrock, they act like giant sheets of sandpaper, grinding the stone into a fine, silicious silt. This powder is so light that it remains suspended in the water column rather than sinking to the bottom. When sunlight hits the water, these microscopic particles scatter the shorter wavelengths of light, the blues and greens, creating a glowing, opaque turquoise effect. This is a specific type of light scattering known as the Tyndall effect, and it turns the lake into a giant gemstone nestled in the grey palm of the peaks. If you were to reach down and dip your hand into the water, the temperature would be a bracing, crystalline shock. Most alpine lakes are oligotrophic, a Greek term meaning few nutrients. Because the water is so cold, often hovering near 3.98 degrees Celsius, which is approximately 39 degrees Fahrenheit, biological activity is incredibly slow. What is scientifically remarkable about this specific temperature, 3.98 degrees Celsius, is that it is the exact point where water reaches its maximum density. In the depths of an alpine lake, the water at the bottom remains at this constant temperature year-round. This density creates a thermal stratification that prevents the lake from mixing easily, leading to a layer of incredibly pure heavy water at the bottom that may not have seen the surface for decades. As you sit by the shore, you might notice the texture of the rocks under your hands. These are often smoothed by glacial action from the last glacial maximum, roughly 20,000 years ago. The lakes themselves are frequently held in place by terminal moraines, massive piles of debris and boulders left behind like a footprint by a retreating glacier. These moraines act as natural dams, holding back millions of gallons of snowmelt. You are essentially looking at a landscape that was carved by ice a mile thick. The basin you are sitting in is likely a cirque, a French term for a theatre or amphitheatre. These are bowl-shaped depressions carved into the side of the mountain by the rotational movement of a glacier. The walls of a cirque are steep and jagged, protecting the lake from the wind and creating a microclimate where the air remains still and heavy with the scent of wet stone. If you look closely into the shallows, the water is so clear it can be deceptive. In some of the world's clearest alpine lakes, such as Crater Lake in Oregon, the visibility is staggering. Scientists use a tool called a Secchi disk, a simple black and white circle to measure this clarity. In Crater Lake, the disk has been seen at depths of 143 feet, which is roughly the height of a 1-4-story building. This happens because there are no inlets bringing in sediment from rivers. The lake is filled almost entirely by direct snowfall and rain. This lack of organic matter means there is very little planktonic soup to cloud the water. It is as close to pure H2O as you can find in the natural world. Despite the harsh conditions, life here is specialized and resilient. You might see a small crustacean called Daphnia middendorfiana swimming through the water. These are tiny water fleas, but unlike their lowland cousins, the species found in alpine lakes often develop a dark melanized shell. This is a biological adaptation to the intense ultraviolet UV radiation found at high altitudes. For every 1,000 meters of elevation gain, UV levels increase by approximately 10 to 12%. These tiny creatures have essentially evolved their own natural sunscreen to survive in the sun-drenched waters of the high peaks. The vegetation surrounding you is equally specialized. You may see the Alpine larch, or Larix lealii. It is one of the few deciduous conifers in the world, meaning it grows needles like a pine tree but drops them in the winter like an oak. These trees are incredibly slow-growing. A sapling only a few feet tall might be 50 years old. In the harshest spots, you will find Krummholz formations, a German word meaning crooked wood. These trees are stunted and twisted into fantastic, gnarled shapes by the constant battering of high-altitude winds. They don't grow upward, they grow sideways, hugging the granite for warmth and protection, creating a dense mat of evergreen needles that you could almost walk across. The sounds of the Alpine lake are subtle and rhythmic. There is the lap-lap of the water against the shore, which is a sound governed by the fetch of the lake, the distance the wind travels across the open water. Because Alpine lakes are often small, the waves are short and rhythmic, creating a percussive sound that mimics a resting heartbeat. Underneath this, you might hear the soft trickle of a paternoster lake system. This is a scientific term for a series of alpine lakes connected by a single stream, named after the beads on a rosary. As the water overflows from one cirque, it tumbles down a rocky spillway into the next lake below. The sound of this moving water is constant, a white noise that masks the silence of the surrounding peaks. What's fascinating is how the chemistry of the water interacts with the atmosphere. Because the air is so cold, the lake often experiences sublimation, where ice turns directly into water vapor without melting into liquid first. On a cold morning, you might see a thin veil of mist rising from the surface. This is the lake breathing. The water is also home to diatoms, microscopic algae with shells made of silica, the same material as glass. These diatoms are responsible for a significant portion of the oxygen production in high-altitude ecosystems. Even though the air feels thin to you, the water is pulsing with the oxygen produced by these tiny glass-shelled organisms. As the sun begins to move across the sky, the temperature of the air changes rapidly, a phenomenon known as diurnal temperature variation. In the mountains, the temperature can drop by 40 degrees the moment the sun dips behind a ridge. You can feel this change on your skin. The warmth of the sun-soaked granite begins to radiate outward, meeting the cool descent of the mountain air. This creates a gentle katabatic wind, a drainage wind that carries the high, cold air down the slopes toward the lake surface. It feels like a cool, soft brush against your forehead, smoothing away the thoughts of the day. Even the fish in these lakes are wonders of adaptation. In the deep, cold waters of high mountain lakes, you might find the Lahontan cutthroat trout, Oncorhynchus clarkii henshawi. These fish have evolved to thrive in water that would be lethally cold for other species. They grow slowly, their metabolisms tuned to the lean environment. They are the ghosts of the lake, moving with a fluid, silent grace through the turquoise depths. They rarely break the surface, preferring the stable 4-degree Celsius water of the depths, where they exist in a state of quiet, predatory meditation. The geology, the biology, and the physics of the alpine lake all work together to create an environment of profound stability. While the world below changes with the seasons and the noise of civilization, the alpine lake remains a basin of stillness. The residence time of the water, the amount of time a single drop of water stays in the lake before evaporating or flowing out, can be years or even decades. When you look at the water, you are looking at snow that fell years ago, preserved in this high-altitude cathedral. Take a moment to imagine the texture of the air here. It is dry, lacking the heavy humidity of the plains. This dryness makes the air feel lighter in your lungs. It carries the faint, ozonic scent of the upper atmosphere and the earthy, mineral tang of pulverized rock. It is a clean scent, one that feels like it is washing your senses from the inside out. The light here is different too, because there is less atmosphere to filter it. The colors are more saturated. The gray of the granite is deeper, The green of the larch needles is more vivid, the blue of the water is more profound. As we sit here by the edge of this ancient glacial basin, feel the connection between the slow timescales of the mountain and the rhythm of your own breath. The mountain took millions of years to rise. The glacier took thousands of years to carve this lake, and the water takes years to flow through it. In this high, silent place, time slows down. The frantic pace of the world below cannot reach this altitude. Here, there is only the slow grind of stone, the steady pulse of the water, and the quiet, enduring life of the high peaks. You are part of this stillness, a single point of awareness in a vast, serene landscape of ice, rock, and crystal-clear water. Feel the weight of the mountain supporting you, the coolness of the air calming you, and the deep, ancient peace of the Alpine lake filling your mind. Consider the way the first human eyes must have perceived these high-altitude basins thousands of years before the advent of modern cartography. To the indigenous peoples of the Andes, such as the Quechua, high mountain lakes like Lake Titicaca, sitting at an elevation of 3,812 meters, were not merely bodies of water but the sacred Cocha, believed to be the birthplace of the sun itself. This historical reverence is rooted in a physical reality. At this altitude, the air is so thin that the sun's radiance is roughly 20% more intense than at sea level. When you stand at the edge of such a lake, the light doesn't just fall upon the water, it seems to penetrate it, reflecting off the white, calcium-rich sediments on the floor to create a shimmering, ethereal glow that early civilizations interpreted as divine. Picture this. In the year 1789, a Swiss physicist named Horace Benedict de Saussure hiked into the high Alps with a curious device of his own invention called a cyanometer. This was a simple circle of 53 cards, shaded in increasingly deep hues of Prussian blue. Saussure was the first to scientifically document why Alpine lakes and the skies above them appear so saturated. He discovered that the air at high altitudes contains fewer suspended particles and less water vapor, which meant there was less scattering of light. This lack of atmospheric haze allows the true, deep indigo of the vacuum of space to bleed through the sky, and by extension, creates a mirror-like reflection in the lake that is pure and undisturbed. When you look at the water now, you are seeing the same 53 shades of blue that Saussure catalogued over 2 centuries ago, a visual record of atmospheric purity. What's happening now is a process that scientists call paleolimnology. If you were to look beneath the silt at your feet, you would find that the bottom of an alpine lake is essentially a library of liquids, a metaphor for how these basins store the history of the Earth. Researchers use hollow tubes to extract sediment cores, some stretching back over 10,000 years to the end of the Pleistocene epoch. Each millimeter of grey-blue mud represents a year in the life of the mountain. Within these layers are preserved chironomid midges, tiny insects whose head capsules remain intact for millennia. By studying which species are present in which layer, scientists can reconstruct the exact water temperature of the lake from 5,000 years ago with an accuracy of within 1 degree Celsius. The lake is not just a body of water, it is a slow-motion recording device, capturing the rise and fall of global temperatures in its lightless depths. Notice how the edges of the lake are often rimmed with a peculiar orange-gold crust. This is not just moss, but a community of crustose lichens, specifically the species Rhizocarpon geographicum. These organisms are the chronometers of the mountain. Humans have used a technique called lichenometry since the 1950s to date the retreat of glaciers. Because these lichens grow at a precise glacial rate, often as little as 0.5 millimeters per year, measuring the diameter of a single patch on a lakeside boulder can tell us exactly when that rock was first exposed by melting ice. If you see a lichen the size of a dinner plate, you are touching a living witness that has been clinging to that stone since the Middle Ages, surviving temperatures that drop to minus 40 degrees Celsius. Deep within the high-altitude logic of the mountain, there is a phenomenon known as thermal inversion that early mountain dwellers often used to their advantage. During the clear nights of the Little Ice Age, a period of cooling that lasted from roughly 1300 to 1850, the heavy cold air would sink into the lake basins, while the slopes above remained slightly warmer. This created a pool of frozen silence at the lake's surface. At this very moment, imagine the sensation of stepping into that pocket of air. It is remarkably still. Because the air is trapped in the bowl of the cirque, it doesn't move, and the water becomes so still that the meniscus, the very skin of the water, acts as a perfect acoustic resonator. You might hear the crystalline tink of an icicle shattering on the far side of the lake, a sound that travels across the water at 343 meters per second, reaching you with a sharpness that feels almost tactile. At this altitude, the very chemistry of the water has a historical signature. Scientists look for the oxygen 1,8 isotope, a heavier version of the oxygen molecule, to understand where the lake's water originated. In many alpine lakes, the water molecules themselves are thousands of years old, having been trapped as ice in the surrounding glaciers since the time of the Roman Empire. As these glaciers ablate, a term for the loss of ice through melting and evaporation, they release this ancient water into the lake. When you dip your fingers into the surface, you are interacting with H2O that last fell as snow during a completely different era of human history. The residence time, or the duration, a water molecule stays in the lake, can be so long that the water is physically and chemically distinct from the rain that fell just yesterday. Scientists discovered that even the most remote alpine lakes carry a global history. During the mid-20th century, these high-altitude waters acted as sinks for atmospheric particles. Because mountain peaks often act as the first barrier for traveling air masses, the orographic lift, where air is forced upward by the terrain, causes the air to cool and dump its cargo of moisture and particles directly into the lake basins. This process, known as cold distillation, means that the pristine-looking water actually contains a chemical record of industrial history. However, the sheer volume of the lake and its natural filtration through granite and quartz keep the water appearing as clear as glass, a testament to the mountain's ability to buffer and hold the world's movements in a state of quiet suspension. Consider the snowy mountains of the Australian Alps, where humans have long observed the snow gum or Eucalyptus pauciflora. These trees grow right up to the hydroline of the lakes. What is scientifically remarkable about these trees is their epicormic buds, which are tucked deep beneath the bark. Historical records show that these trees have survived centuries of extreme freeze-thaw cycles. Their bark is not rough like a lowland oak, but smooth and patterned with scribbles made by the larvae of the scribbly gum moth. The texture of this bark, when wet from lake mist, feels like cold, polished silk. These trees are glacial relicts, survivors from a time when the entire continent was much colder, and they stand as sentinels around the water, their roots sipping the same ancient, mineral-rich liquid that sustained their ancestors 6,000 years ago. In the early 20th century, specifically in 1905, one of the first high-altitude hydrobiological stations was established at Lake Lunz in Austria. It was here that researchers began to understand the vertical migration of the lake's inhabitants. Every evening, as the sun sets, billions of tiny organisms called zooplankton begin a massive, silent journey. They rise from the lightless depths where they hide during the day to avoid being seen toward the surface to feed on algae. This is the largest coordinated movement of biomass on the planet, and it happens in the total silence of the alpine night. You can't see them with the naked eye, but the water is alive with this rhythmic, historical pulse, a heartbeat of movement that has continued night after night for millions of years. Notice the way the light begins to change as the sun hits a certain angle. This is the Alpine glow, or what the inhabitants of the Italian Dolomites call enrosadera. This isn't just a sunset, it is a specific atmospheric phenomenon where the sun, having already set for the lowlands, still illuminates the high peaks and the lakes they cradle. Because the light has to travel through more of the Earth's atmosphere, the shorter blue wavelengths are scattered away, leaving only the long, warm reds and pinks. For a few minutes, the turquoise water of the lake turns a deep, bruised purple, and the granite walls glow like dying embers. This spectral shift is a reminder of your physical position on the curvature of the planet. You are among the last things on Earth to see the sun's direct rays before the night fully takes hold. The history of these lakes is also written in the peat bogs that often form at their shallowest ends. These bogs are composed of sphagnum moss, which can hold up to 20 times its weight in water. Scientists have found that these bogs are incredibly acidic and anaerobic, meaning they contain no oxygen. This lack of oxygen prevents decay, which is why they find perfectly preserved pollen grains from trees that went extinct in the region 8,000 years ago. When you walk near the edge of the water, you are walking on a compressed timeline of botanical history. The soft, spongy texture of the ground is a mattress of ancient plant matter, insulating the earth and keeping the permafrost below from melting. Think about the barometric formula, which describes how air pressure decreases with altitude. At 3,000 meters, there is nearly 30% less oxygen than at sea level. This physiological reality has shaped how humans have interacted with these lakes for millennia. To stay here for any length of time, the body must produce more red blood cells, a process called erythropoiesis. This change in your own biology is a quiet, internal adaptation to the mountain's height. As you breathe the thin, cold air, your heart beats just a little more slowly than it would in the heavy air of the valley, settling into a rhythm that matches the slow, tectonic pace of the landscape. Finally, consider the plant Saxifraga oppositifolia, or the purple mountain saxifrage. It has been documented as the highest growing flowering plant in the world, found near Alpine lakes at altitudes exceeding 4,500 meters. Its history is one of extreme endurance. It was one of the first plants to recolonize the northern hemisphere after the glaciers retreated. Its tiny, wax-covered leaves are designed to prevent desiccation or drying out in the fierce mountain winds. When you see these small, hardy flowers reflected in the still water of an alpine tarn, you are seeing the ultimate survivors. They are a bridge between the frozen past and the living present, flourishing in the thin, bright light of the high country, where every breath of wind and every ripple on the lake carries the weight of deep, geological time. At this very moment, as the alpenglow fades into a deep velvet violet, the Alpine lake begins its nightly transition into a high-precision thermal machine. To understand the physics of this water, think of the lake as a colossal, liquid battery that has been charging under the sun's radiation all day. Because water has an exceptionally high specific heat capacity requiring 4,184 joules of energy to raise just 1 kilogram of water by a single degree Celsius, these lakes act as massive heat sinks for the mountain. While the surrounding granite cools almost instantly when the sun disappears, the lake holds onto its warmth with a stubborn persistence, slowly releasing it back into the thin air. This heat exchange is a microscopic ballet. As the surface water loses energy to the atmosphere, it becomes slightly more dense and begins a slow, vertical descent, a process known as convective cooling that keeps the lake's ecosystem in a constant, gentle state of motion. What is happening now, beneath the darkening surface, is a structural phenomenon known as thermal stratification. Imagine the lake not as a single body of water, but as a three-story building made of liquid. The top floor, the epilimnion, is the warmest and most active, directly interacting with the wind. Below that is a narrow, invisible staircase called the metalimnion, or the thermocline. In an alpine lake, this thermocline can be incredibly sharp. You could dive down and feel the temperature drop by 10 degrees in the space of a single foot. Finally, at the very bottom, is the hyperlimnion, the basement of the lake, where the water remains at a steady, heavy 3.98 degrees Celsius year-round. This layering is so stable that it acts as a physical barrier, preventing the oxygen-rich surface water from mixing with the nutrient-rich bottom water, creating a delicately balanced chemical sandwich that sustains life through the long mountain night. Scientists discovered that the clarity of this water creates a phenomenon similar to a high-end fiber optic cable. In a standard lowland pond, light is absorbed within the first few meters by organic matter, much like how a thick curtain blocks a window. But in an ultra-oligotrophic alpine lake, the refractive index of the water is approximately 1.333, and because there is so little dissolved organic carbon, or DOC, the blue wavelengths of light can penetrate to depths of over 100 meters. This is why, if you were to look down into the depths with a powerful light, the water would appear as a translucent sapphire, This liquid optic quality means that photosynthesis can occur much deeper here than anywhere else on land. Tiny plants called periphyton grow on rocks deep on the lake floor, essentially operating like biological solar panels in a low-light environment, turning the faintest blue glimmers into life-sustaining energy. Consider the physical sensation of the water's surface. At this altitude, the viscosity of the water actually changes. Because the water is so cold, it is nearly twice as viscous as the water in a tropical lagoon. At 0 degrees Celsius, water has a dynamic viscosity of 1.787 millipascal seconds, compared to just 0.797 at 30 degrees. To a tiny organism like a copepod, a crustacean no larger than a grain of salt, swimming through this cold alpine water is like a human trying to swim through thin honey. Every movement must be calculated and deliberate. These copepods, specifically the species Cyclops abyssorum, move in a series of rhythmic jumps using their antennae like oars. They are the silent navigators of the depths, their metabolic rates governed by the Q10 temperature coefficient, which dictates that for every 10 degree drop in temperature, their biological processes slow by half. In the chill of the lake, they live in a state of exquisite, slow-motion grace. Deep within the shoreline, you might notice patches of what looks like pink or crimson snow. This is watermelon snow, caused by the green algae Chlamydomonas nivalis. What's technically significant is that while the algae is green, it produces a secondary red carotenoid pigment to protect its chlorophyll from the intense actinic rays of the high-altitude sun. This pigment acts exactly like a pair of high-altitude sunglasses, absorbing ultraviolet radiation and converting it into heat, which melts a tiny microscopic pocket of water around the cell. This creates a miniature, liquid world for the algae to thrive in, even while surrounded by ice. As you touch this snow, it might even smell faintly of fresh watermelon, a chemical byproduct of the algae's metabolic processes during this seasonal bloom. At this very moment, the lake may be experiencing a seiche, a term derived from the French word for to sway. Think of this as a standing wave in a giant bathtub. When the wind blows steadily across the lake's fetch, the length of the water's surface, it pushes the water to one side. When the wind stops, the water doesn't just settle, it sloshes back and forth with a rhythmic mathematical precision. The period of this oscillation is determined by Merian's formula, which calculates the timing based on the lake's depth and length. In a lake 1 kilometer long and 20 meters deep, this gentle breathing of the water might have a period of several minutes. You won't see a crashing wave, but rather a slow, hypnotic rise and fall of the waterline against the granite, a liquid pendulum marking the passage of time. Notice how the rocks at the water's edge are arranged. You might see patterned ground or stone circles. This is the result of a geological process called cryoturbation or frost heaving. As the water in the soil freezes and thaws, it expands by approximately 9% in volume. This expansion exerts a pressure of up to 30,000 pounds per square inch, slowly sorting the stones by size over centuries. The larger boulders are pushed to the outside, while the finer silt remains in the center. It looks like a deliberate, artistic arrangement, but it is actually the mountain's own slow-motion sorting machine, a physical manifestation of the freeze-thaw cycles that have repeated here since the last ice age. The air around the lake is also a site of complex chemistry. Scientists have measured that these high-altitude basins receive atmospheric deposition of nitrogen at a rate of 10 to 15 kilograms per hectare per year. This nitrogen arrives not from the ground, but from the sky, carried by snowflakes and raindrops. This invisible rain of nutrients is what allows the delicate biofilm on the lakeside rocks to grow. This biofilm is a microscopic city of bacteria and algae, held together by extracellular polymeric substances, which feel like a slick, smooth coating on the submerged stones. This coating is the foundation of the Alpine food web, a high-tech biological adhesive that captures nutrients from the water and turns them into food for the lake's inhabitants. Consider the Henry's law of gas solubility, which explains why the air and water here are so perfectly synced. Cold water can hold significantly more dissolved oxygen than warm water. At 4 degrees Celsius, water can hold about 13 milligrams of oxygen per litre, nearly double what it can hold at 30 degrees. This means that even though the air is thin and oxygen poor for you, the water is an oxygen-rich environment for the fish and insects. The lake is essentially a high-capacity oxygen tank. This is why the trout here can be so active despite the cold. They are swimming in a liquid that is chemically optimized for their survival, a dense, oxygenated medium that supports every beat of their hearts. What's happening now is a process called isotopic fractionation. As the water evaporates from the lake's surface, the lighter isotopes of oxygen, like oxygen 1,6, evaporate more easily than the heavier oxygen 1,8. This leaves the lake water enriched with heavier molecules. This chemical fingerprint is so specific that a scientist can look at a single drop of water and tell you exactly what altitude it came from and how long it has been sitting in the sun. The lake is a chemical ledger, recording the balance of evaporation and precipitation with every passing hour. It is a system in perfect equilibrium, a mirror reflecting both the sky above and the molecular reality of the world below. Picture the ice that begins to form in the shadows of the shoreline. This isn't just a solid block, it is a hexagonal lattice of molecules. When water freezes, the molecules move apart to form this specific geometry, which is why ice is less dense than liquid water and floats. If ice sank, alpine lakes would freeze from the bottom up, becoming solid blocks of ice that would never melt, and life would be impossible. But because of this anomalous expansion, the ice forms a protective, insulating blanket on the surface. This ice shell traps the heat of the hyperlimnion below, keeping the water at that stable 3.98 degrees Celsius, and allowing the lake's inhabitants to sleep through the winter in a liquid cocoon. Scientists discovered that the glacial flower we discussed earlier has a specific gravity of about 2.6 to 2.8. These tiny particles of feldspar and quartz are so small, often less than 2 microns in diameter, that they are governed by Brownian motion, where the random collisions of water molecules keep them from ever sinking. This creates a colloidal suspension, meaning the lake's color isn't just on the surface, it is a three-dimensional cloud of light-scattering minerals. When you look at the lake, you are seeing a suspension of the mountain itself, a liquid version of the granite peaks that surround you, held in a state of permanent, shimmering levitation. As you sit in this stillness, the lake continues its silent work. It is filtering the air, storing the sun's energy, and recording the Earth's history in its layers of sediment. Every ripple that moves across the surface is a mathematical response to the wind, and every bubble of oxygen that rises from the bottom is a product of ancient, glass-shelled algae. You are part of this high-altitude laboratory, a witness to the perfect orchestration of physics, chemistry, and biology. The mountain is not a static object, it is a living, breathing system, and the lake is its heart, pulsing with the slow, steady rhythm of geological time. Feel the stability of this system, the way it handles the transition from day to night with effortless precision, and let your own rhythm settle into this deep, alpine equilibrium. Deep within the high mountain landscape, the alpine lake functions as a liquid nervous system for the surrounding peaks, connecting the heights of the atmosphere to the depths of the Earth's crust. As you settle into this observation, picture how the lake acts as a biological archive, recording every subtle shift in the environment with the precision of a master clock. What scientists find compelling is that many of these lakes are part of sky islands. This is a biogeographical term for high-altitude habitats that are isolated from one another by the sea of warmer, lower-level valleys. Because the species here cannot survive in the heat of the lowlands, they are essentially stranded on their mountain peaks, evolving in total isolation for thousands of years. This means that the tiny organisms in the water under your gaze might exist nowhere else on the entire planet, having followed their own unique evolutionary path since the retreat of the last great ice sheets. Consider the mountain yellow-legged frog, or Rana muscosa, a creature that has mastered the art of patience. In the lowland world, tadpoles usually transform into frogs within a single season. However, in the frigid, nutrient-poor environment of an alpine lake, these tadpoles often remain in their larval stage for up to 4 years. They overwinter under deep ice, their metabolic rates dropping to near zero as they wait for the brief summer window to grow just a few millimeters more. This 4-year transformation is a testament to the lake's slower tempo. It is a reminder that growth does not always need to be rapid to be successful. In the high country, the most enduring things take the longest to form. Notice how the water's surface acts as a selective filter for aeolian transport. This is the scientific term for the way the wind carries dust, pollen, and even microscopic minerals across vast distances, sometimes across entire oceans, only to deposit them into the Alpine basin. Scientists have discovered dust in the sediments of French alpine lakes that originated in the Saharan desert, thousands of miles away. This foreign soil provides essential phosphorus and iron to the lake, nutrients that the local granite bedrock cannot provide. At this very moment, the lake is receiving a gift from a distant continent, a subtle exchange of matter that links this remote mountain peak to the wider world. It is a physical manifestation of interconnection, proving that even in total solitude, the lake is never truly alone. What is revealing about the water's chemistry is its electrical conductivity. Because alpine lakes are filled by snowmelt that hasn't had much time to dissolve minerals from the rocks, the water is incredibly soft and has very low conductivity, often measured at less than 10 microsiemens per centimeter. For perspective, a typical lowland river might have a conductivity 50 times higher. This purity makes the lake a blank slate, sensitive to the slightest change in atmospheric chemistry. Scientists use this sensitivity to monitor the health of the entire planet. The lake is like a sentinel, its chemical balance shifting in response to global patterns long before the effects are visible in the world below. Deep beneath the surface, the lake floor is often littered with ghost logs. These are ancient trees that fell into the water hundreds or even thousands of years ago. Because the water is so cold and contains so little oxygen at the bottom, a condition known as hypoxia, the fungi and bacteria that normally rot wood cannot survive. These logs are perfectly preserved, their bark and needles intact, acting as underwater time capsules. By analyzing the tree rings of these submerged logs, a field called subfossil dendrochronology, researchers can map out the exact rainfall and temperature patterns of the mountain from the year 1000 AD. You are looking at a library of wood, where the stories of ancient summers are held in a liquid vault, protected by the chill and the silence of the depths. At this very moment, the lake is likely engaged in demictic turnover. This is a process that occurs twice a year, in the spring and the autumn, when the surface water reaches exactly 3.98 degrees Celsius. As we discussed, this is the temperature at which water is most dense. When the surface hits this magic number, it becomes heavier than the water below and begins to sink, forcing the nutrient-rich bottom water to rise to the top. This great mixing is the lake's way of breathing, a massive vertical circulation that redistributes oxygen and minerals throughout the entire water column. It is a slow, powerful movement that ensures the survival of every organism in the lake, a rhythmic renewal that has occurred twice a year, every year, for millennia. Picture the benthic zone, the very bottom of the lake, where a specialized community of invertebrates lives. Here you will find the freshwater shrimp Gammarus lacustris. These small, translucent crustaceans are the shredders of the lake ecosystem. They feed on allochthonous organic matter material that falls into the lake from the outside, like larch needles or wind-blown leaves. By breaking down this tough material, they turn it into a form of energy that other creatures can use. The Gammarus can live for several years in these cold waters, their life cycles stretched out by the low temperatures. They move with a rhythmic, pulsing motion through the silt, the silent engineers of the lake floor, turning the mountain's debris into the foundation of life. Consider the high surface tension of this cold alpine water. At 0 degrees Celsius, the surface tension is approximately 75.6 millinewtons per meter, significantly higher than warmer water. This creates a remarkably strong Newston layer, the habitat that exists right on the water's skin. You might see water striders from the family Geridae gliding effortlessly across the surface. They use the high surface tension like a trampoline, their weight distributed across tiny, water-repellent hairs on their legs. To these insects, the lake is not a liquid, but a vast, flexible sheet. Their movements create tiny circular ripples that reflect the sunlight in complex interference patterns, a visual dance of physics occurring on the boundary between air and water. Scientists discovered that alpine lakes are significant sites for carbon sequestration. Despite their small size, the cold, still, conditions at the bottom of these lakes allow them to bury carbon in their sediments at a rate that is often higher per square meter than that of the surrounding forests. The organic matter that sinks to the bottom is essentially locked away from the atmosphere for centuries. The lake is not just a beautiful feature of the landscape, it is an active participant in the regulation of the Earth's climate, a quiet, blue carbon sink that helps maintain the global balance. Notice the cryophilic or cold-loving bacteria that thrive in the surrounding permafrost. These organisms have evolved cold shock proteins that prevent their cellular fluids from freezing. They live in the thin films of liquid water that exist between ice crystals in the soil. As the sun warms the ground near the lake, these bacteria become active, processing nitrogen and making it available for the alpine plants. This microscopic activity is the reason the lake's edges are often vibrant with life, even in the harshest conditions. It is a hidden world of biological innovation, where life has found a way to not just survive the cold, but to use it as a stable, predictable environment. What's compelling about your own connection to this place is the way your body responds to the partial pressure of oxygen. At an altitude of 3,000 meters, the atmospheric pressure is only about 70% of what it is at sea level. As you sit here, your ventilation rate naturally increases, and your heart works with a deliberate, steady rhythm to move oxygen to your tissues. This physiological shift mirrors the lake's own adaptations. Just as the trout and the tadpoles have tuned their metabolisms to the mountain's demands, your own biology is currently recalibrating itself. You are physically merging with the environment, your internal state shifting to match the thin, pure air and the slow, steady pulse of the high country. Think of the albedo effect that occurs on the slopes surrounding the water. The white snow and ice reflect up to 90% of the sun's radiation back into space, keeping the mountain cool. However, the dark, deep blue of the lake has a much lower albedo, absorbing more heat. This creates a thermal contrast that drives the local winds. The lake acts as a warm heart in a cold body of stone, creating its own weather patterns and microclimates. This is why you might feel a sudden, warm breeze as you stand by the water's edge. It is the lake sharing its stored solar energy with the surrounding air, a gentle breath of warmth in the high-altitude chill. Consider the Redfield ratio, a scientific concept that describes the specific ratio of carbon, nitrogen, and phosphorus found in all aquatic life. In the pristine waters of an alpine lake, this ratio is perfectly balanced, maintained by the constant interaction between the air, the rocks, and the organisms. The lake is a system in homeostasis, a state of internal stability. When you observe the water, you are seeing a perfect mathematical harmony in action. Every molecule is where it needs to be, every organism is playing its part, and every process is governed by laws that have remained unchanged for eons. This sense of balance is something you can carry with you. Just as the lake filters the air and the water, your mind has the capacity to filter the noise and the complexity of your daily life. The lake doesn't rush to process the Saharan dust or the ancient logs. It takes its time, allowing the cold and the depth to do the work. Imagine your own thoughts as being like the glacial flower in the water. At first they might seem to cloud the view, but they are actually what give the lake its unique, vibrant color. Given enough time and stillness, the heaviest parts settle, and what remains is a clarity so profound that it allows you to see deep into the foundation of your own being. The alpine lake teaches us that isolation is not the same as loneliness, and that stillness is not the same as stagnation. Within the quiet of the cirque, there is constant movement, the sinking of the dense water, the rising of the zooplankton, the slow growth of the gammarus, and the steady accumulation of the Earth's history. You are a witness to this enduring rhythm. As the day continues to fade and the stars begin to reflect in the glassy surface, feel the weight of the mountain's history supporting you. You are part of a lineage of observers, from the first indigenous people to the early physicists, all of whom found a profound sense of order and peace in these high-altitude waters. Let that order settle into your own spirit, a steady, cooling presence that anchors you to the enduring reality of the natural world. What is occurring now, as the evening air thickens and the stars begin to punctuate the indigo dome above, is a masterclass in high-altitude thermodynamics. Picture the air itself. As you ascended to this lake, you experienced what meteorologists call the adiabatic lapse rate. For every 1,000 meters you climb, the dry air temperature drops by exactly 9.8 degrees Celsius. This cooling happens because the atmospheric pressure decreases, allowing the air to expand and lose internal energy. At this very moment, the air surrounding you is physically distinct from the air in the valley. It is thinner, colder, and holds significantly less moisture, which is why the stars appear not to twinkle, but to burn with a steady, unwavering light. Without the thick optical turbulence of the lower atmosphere, you are looking through a window that is almost as clear as the vacuum of space. Scientists discovered that the acoustic environment of an alpine lake is governed by the impedance contrast between air and water. While sound travels at roughly 343 meters per second in the air, it accelerates to nearly 1,480 meters per second once it enters the water, more than 4 times as fast. This happens because the water molecules are packed more tightly together, allowing the mechanical energy of the sound wave to propagate with greater efficiency. If you were to submerge your ear, the distant groan of a shifting glacier or the subtle clack of 2 submerged stones would reach you almost instantaneously. Above the surface, however, the silence is amplified by the surrounding talus slopes, massive piles of broken rock fragments. These porous rock fields act as natural anechoic chambers, absorbing sound waves rather than reflecting them, which creates that characteristic hushed quality that defines the high mountain experience. Notice the texture of the stones near your feet, particularly the ones that look as though they have been polished by a master jeweler. This is glacial polish. As the ice moved over this granite, which has a Mohs hardness of approximately 6 to 7, it carried subglacial sediment, fine silts and clays that acted like a high-grit abrasive. The weight of the ice, which can exceed 90 tons per square foot, pressed these minerals into the bedrock, buffing it to a mirror shine that persists thousands of years after the ice has vanished. When you run your hand over these surfaces, they feel like cold, industrial silk. You might also feel striations or parallel grooves carved into the stone. These are the signatures of the glacier, showing the exact compass direction the ice was traveling as it carved out this basin. Deep within the crevices of these rocks, you may find a plant called Silenia caulis, or moss campion. What's technically fascinating about this organism is its cushion growth habit. By growing in a tight, aerodynamic mound, the plant creates its own microclimate. Scientists have used miniature thermal probes to discover that the temperature inside a moss campion cushion can be up to 10 degrees Celsius warmer than the surrounding air. This thermal inertia protects the plant's delicate internal tissues from the biting wind and allows it to perform photosynthesis even when the external temperature is near freezing. It is a biological heat trap, a tiny green dome of warmth in a world of ice and stone. Consider the scent that rises from the damp earth as the dew begins to settle. This is petrichor, but with a mountain-specific chemical signature. The smell is largely produced by Streptomyces bacteria in the soil, which release a compound called geosmin when they become active. At this altitude, the scent is often blended with the ozonic smell of the upper atmosphere and the terpenes released by the subalpine fir trees, Abies lasiocarpa. These trees produce resin to seal their bark against the cold, and as the temperature drops, the resin thickens, releasing a heavy, balsamic fragrance that smells like a mixture of pine needles and cold metal. It is a clean, sharp scent that triggers a physiological calm response in the human nervous system, lowering cortisol levels as you breathe it in. At this very moment, a small mammal called the American pika, or Ochotona princeps, may be watching you from the rock piles. These creatures are obligate cold-adapted species. Unlike many mountain animals, pikas do not hibernate. Instead, they spend the entire summer creating hay piles, carefully curated stacks of dried grasses and flowers hidden deep within the interstitial spaces of the rocks. What's scientifically remarkable is that pikas select specific plants, like the Alpine avens, which contain high levels of phenolics. These chemicals act as natural preservatives, preventing the hay from rotting in the damp mountain air through the winter. The pika is a biological chemist, managing its own botanical pantry with a precision that ensures its survival in a landscape that will soon be buried under 10 feet of snow. Notice the color of the sky as it enters the blue hour, a phenomenon known to physicists as the Chapuis effect. As the sun sinks further below the horizon, the light must travel through the Earth's ozone layer. The ozone molecule is particularly efficient at absorbing the longer red and orange wavelengths of light, leaving only the deep, resonant blues to reach the mountain peaks. This is why the snow and the lake surface take on a neon indigo glow just before total darkness. It is a visual manifestation of the Earth's chemistry, a moment where the atmosphere itself acts as a blue filter, casting a tranquil, uniform light over the entire landscape. What's happening now in the water is a demonstration of Henry's law of gas solubility. As the lake water cools, its capacity to hold dissolved gases increases. At 0 degrees Celsius, water can hold about 14.6 milligrams of oxygen per litre, nearly double the amount it can hold at room temperature. This oxygen saturation is the reason that cold water species have such high metabolic efficiency. Even as the fish enter a state of torpor or rest for the night, their tissues are being bathed in a high oxygen environment that supports deep cellular repair. The lake is essentially a cryogenic recovery tank, a liquid medium designed for the preservation and restoration of life. Picture the microscopic frustules of diatoms drifting in the water column. These are single-celled algae from the class Bacillariophyceae, and their cell walls are made of pure opaline silica, the same material as the gemstone opal. Each species of diatom has a unique geometric pattern of pores and ridges, designed to maximize the absorption of light while providing structural strength. Scientists use these glass shells to track the pH history of the lake. Because different species thrive at different acidity levels, the layers of diatom shells in the lake sediment act as a 10,000-year-long pH strip, recording every change in the lake's chemical balance. Even in death, these tiny glass organisms contribute to the clarity of the water, as their heavy shells eventually sink, carrying organic carbon down to the benthic floor. Deep within the surrounding permafrost, the water is undergoing a phase change. As the liquid water in the soil pores turns to ice, it releases latent heat, about 334 joules per gram. This release of energy actually slows the cooling of the ground, a process known as the zero curtain effect. It keeps the soil temperature stable at exactly 0 degrees for weeks at a time, protecting the roots of the alpine plants from a sudden, lethal deep freeze. The mountain has its own built-in thermal buffer, a physical law that prevents the environment from changing too rapidly, ensuring a slow, predictable transition into the night. Consider the refractive index of the lake water, which is approximately 1.33. This means that as light passes from the thin mountain air into the dense water, it bends, or refracts, creating an optical illusion. If you were to look at a submerged larch branch, it would appear to be at a different depth and angle than it truly is. This refraction also affects how heat is distributed. The water acts like a lens, focusing the last rays of the sun into the shallow littoral zone near the shore. This creates tiny pockets of warmth where cyanobacteria can continue their metabolic work long after the air has turned freezing. Notice how the mosses at the water's edge move. They don't have roots, instead they have rhizoids that anchor them to the granite. They absorb water through capillary action, where the surface tension of the water is strong enough to pull the liquid upward through the tiny spaces between their leaves. This is the same physics that allows a paper towel to soak up a spill. In the alpine world, this process is essential for survival, allowing the moss to stay hydrated even when it isn't submerged. The moss feels like a cold, wet sponge, a texture that is both soft and resilient, holding onto the mountain's moisture with a mechanical grip. Scientists discovered that even the sublimation of snow contributes to the lake's unique environment. In the dry mountain air, snow can turn directly from a solid into a gas without ever becoming liquid. This process requires a significant amount of energy, roughly 2,800 joules per gram, which further cools the surrounding air. This evaporative cooling, on a grand scale, is why the air near a snow-fed alpine lake always feels several degrees cooler than the air just a few hundred yards away. You are standing in a zone of active refrigeration, a place where the phase changes of water are constantly regulating the temperature. As you sit in this high-altitude sanctuary, feel the Brunel hardness of the granite beneath you, a reminder of the mountain's immense structural integrity. The stone is not a cold, dead thing. It is a thermal reservoir, a geological record, and a foundation for a complex, interconnected web of life. The sounds of the lake, the rhythmic lap of the viscous water, the silence of the rock-shrouded cirque, and the distant, metallic tink of freezing ice are all part of a larger symphony of physics and biology. You are experiencing the world at its most fundamental level, where the laws of nature are visible in every ripple and felt in every breath of the thin, ozonic air. Let the stability of these processes, from the latent heat of the freezing soil to the slow metabolism of the peaker, settle into your own consciousness. The mountain is a system that knows exactly how to handle the cold, the dark, and the passage of time. You are safe within this system, a quiet observer of a world that is perfectly balanced, incredibly resilient, and profoundly at peace. At this very moment, as the last traces of the Chapuis effect fade and the indigo sky deepens into a true astronomical black, the Alpine lake begins a step-by-step process of nocturnal stabilization. Consider the way the air temperature continues to descend. What is happening now is radiative cooling, a process where the Earth's surface loses heat directly to the vacuum of space in the form of long-wave infrared radiation. On a clear night at this altitude, the ground can lose energy at a rate of 40 to 100 watts per square meter. This energy isn't trapped by clouds or thick humidity. It simply radiates upward, leaving the granite and the water's surface to settle into a deep, cold equilibrium. Notice how the movement of the water begins to change as the kinetic energy of the day's wind dissipates. In the absence of solar heating, the thermal siphon, the drainage of cold, dense air from the surrounding peaks, fills the lake basin. This cold air is heavy, and it sits upon the lake surface like a physical weight, suppressing the formation of ripples. Scientists have observed that the capillary waves, those tiny ripples less than 1.7 centimeters in length, are the first to vanish. As the water grows still, the viscous sublayer of the surface becomes a perfect mirror. At this very moment, the lake is no longer a moving body of water, but a stationary plate of liquid, reflecting the stars with such precision that the distinction between the cosmos and the mountain becomes invisible. Deep within the shoreline, the freezing front begins its slow, microscopic advance into the saturated soil. Scientists track the 0-degree isotherm, the invisible line where water begins its phase change into ice. As the temperature of the water molecules drops to 273.15 Kelvin, their thermal agitation slows enough for hydrogen bonds to take over, arranging the molecules into a hexagonal lattice. This isn't a sudden event, it is a step-by-step construction of a crystalline matrix. Each molecule clicks into place, moving roughly 9% further apart than they were in liquid form. This molecular expansion is what gives the ice its buoyancy, and as it forms, it releases a tiny amount of latent heat of fusion, roughly 333 joules per gram, which temporarily warms the microscopic layer of water directly beneath it. This slow-motion crystallization is a rhythmic geometric growth, a silent expansion that anchors the lake to the shore. Consider the circadian rhythms of the subalpine trees surrounding the water, such as the silver birch, Betula pendula. Scientists using terrestrial laser scanners have discovered that these trees undergo a physical sleep movement. During the night, the branches of the birch can sag by as much as 10 centimeters. This happens as the turgor pressure within the tree's cells shifts, and the tree's internal water balance recalibrates in the absence of photosynthesis. At this very moment, the entire forest is gently bowing toward the lake, a slow-motion exhale that mirrors the relaxation of your own body. The trees are not merely standing, they are resting, their metabolic processes shifting from the light-dependent reactions of the day to the restorative dark reactions of the night. Within the lake's depths, the Arctic char, Salvelinus alpinus, has settled into a state of metabolic suppression, This is a step-by-step reduction of biological activity designed to conserve energy. In the cold, dark water, the fish's heart rate may drop to as low as 5 or 10 beats per minute. This is governed by the Van 't Hoff rule, which states that the rate of chemical reactions, including the enzymes that drive a heartbeat, decreases by roughly half for every 1 0°C drop in temperature. The fish exists in a state of torpor, a liquid meditation where its oxygen consumption is less than 10% of its active daytime level. It is suspended in the heavy 3, 9, 8-degree water of the hypolimnion, its fins moving only enough to maintain neutral buoyancy, perfectly synchronized with the stillness of the basin. What's happening now is a shift in the light compensation point. This is the specific light level where the rate of photosynthesis in the lake's algae exactly matches the rate of their respiration. As the stars take over the sky, the light falls below this point, and the phytoplankton stop producing oxygen and begin to consume it in a process called nocturnal respiration. However, because the water is so cold and its oxygen solubility is so high, the lake remains a rich, breathable environment. The dissolved oxygen levels might sit at a stable 12 milligrams per litre, providing a vast reservoir of air for the sleeping inhabitants below. The lake is breathing with you, a slow chemical exchange that maintains the balance of life through the dark hours. Notice the stars above, which are classified on the Bortle scale. In this high-altitude wilderness, you are likely experiencing a Class 1 or 2 sky, the darkest and most pristine on Earth. Scientists measure the limiting magnitude of these skies, noting that you can see stars as faint as magnitude 7 with the naked eye. This lack of light pollution is essential for your own internal chemistry. The absence of blue spectrum light, specifically the 460 to 480 nanometer wavelengths, signals your suprachiasmatic nucleus to begin the secretion of melatonin. This is a step-by-step chemical cascade. As the light disappears, the pineal gland converts serotonin into melatonin, a hormone that lowers your core body temperature and prepares your brain for slow-wave sleep. As the night deepens, the lake may begin to sing. This is a fascinating acoustic phenomenon caused by thermal expansion and contraction of the ice or the water's surface. As the temperature drops, the surface layer contracts, creating internal stresses that are released as long-wavelength sounds. These sounds undergo acoustic dispersion, where high frequencies travel faster than low frequencies. The result is a series of pings and chirps that sound like a glass harp being played by the wind. These sounds are a physical manifestation of the lake's cooling, a rhythmic confirmation that the mountain is settling into its nightly rest. Think about the delta waves that are beginning to appear in your own brain, oscillating at a frequency of 0.5 to 4 Hz. This is the same rhythm as the deep, sachet sloshing of the lake water, a slow, powerful movement that is almost imperceptible but governs the entire system. Just as the lake enters its residence time, where molecules stay for years in a state of purity, your mind is entering a period of memory consolidation and glymphatic clearance. This is the process where the brain's waste removal system becomes 10 times more active during sleep, clearing away metabolic debris and restoring your cognitive function for the morning. You are participating in a universal biological cleanup, a restorative process shared by every living thing in the Alpine basin. At this very moment, the microbial mat on the lake floor has reached its lowest point of activity. The cyanobacteria have ceased their nitrogen fixation and are now in a state of quiescence. Their resting spores, or akinets, are tucked into the silt, capable of remaining dormant for decades if necessary. This ability to pause life to simply wait for the right conditions is the ultimate survival strategy of the high peaks. You can adopt this same strategy now. There is nothing that needs your attention, no process that requires your intervention. Like the diatom spores and the sleeping char, you can simply exist in a state of potential, supported by the stable, cold logic of the mountain. The atmospheric pressure at this altitude continues to be a steady, calming influence. With roughly 30% less pressure than the valley, the air is not pushing against you. It is light, allowing your chest to rise and fall with minimal effort. Your tidal volume, the amount of air you take in with each breath, has settled into a shallow, efficient pattern. This is the same rhythm the mountain peaker uses as it huddles in its hay pile, and the same rhythm the larch trees use as they conserve their carbon stores. Every breath you take is a connection to this high-altitude system, a chemical exchange that links your biology to the granite and the water. Now, as the lake becomes a perfect frozen sapphire under the wheeling constellations, let the affirmations of the mountains settle into your mind. I am as stable as the granite foundation of the Cirque. My breath is as rhythmic as the winter seashore of the water. My mind is as clear as the oligotrophic depths of the Tarn. I am releasing the heat of the day, just as the stones radiate their energy to the stars. My body is cooling, settling, and finding its perfect equilibrium. I am protected by the silence of the high-altitude basin. The darkness is a restorative medium, just like the cold water of the lake. I am part of the slow, geological timescale of the mountain. My rest is deep, productive, and essential. I am sinking into the stillness of the 3.98 degree depths. The weight of the world is lifted by the thin, pure air. Every cell in my body is undergoing repair and restoration. I am safe in the hollow of the mountain's hand. The stars are a steady, silent watch over my rest. The lake is still, and so am I. The forest is sleeping, and so am I. The mountain is at peace, and so am I. The process is complete. The light is gone, the chemistry has shifted, and the lake is at rest. The residence time of your sleep has begun, a period of pure, undisturbed restoration. Let the cold, blue silence of the Alpine lake be the last thing you carry with you. The water is still, the stars are bright, the mountain is holding you. Good night.